So, please now understand that by this Gibbs free energy I find delta G, from delta G I find Kp directly. Now, this is another expression which I have got for Kp in terms of partial pressure, but in this case I do not know the right hand side. So, I can generate one equation which will give something in terms of mole fraction. So, for that I try to define mole fraction of the species as partial pressure of the species Pi divided by the total pressure P at which the combustion reaction is taking place. So, here I am in this expression I have Pi divided by P naught. So, now that ratio is written as Xi, that is the mole fraction into P by P naught. P is the total pressure at which reaction is taking place, and P naught is the atmospheric pressure or standard pressure. Okay, now you can say that if the combustion itself is taking place at the atmospheric pressure, then Xi will be equal to Pa by P naught, or else you have to apply this ratio. Okay, so please understand what we are doing here. Gibbs free energy, this is basically for a constant pressure reactor, or when the combustion taking place, the pressure remains almost constant. Please understand that the pressure will locally vary based upon dynamic pressure, etc. However, the overall pressure is not going to be varied, that is at P. Reaction pressure is P. So, for constant pressure reaction, for constant pressure reaction, you will see that the Gibbs free energy can be defined as H minus Ts and is a very useful property for us. And based upon this property, I define molar Gibbs free energy change delta G as the Gibbs free energy of the products minus the Gibbs free energy of the reactant at a given temperature and pressure, atmospheric pressure P naught. Now, based upon the definition, see, for example, if the derivation is there, you can refer any combustion textbook to get this derivation. We can derive two expressions for Kp, one with respect to delta G, one with respect to the partial pressure of the species present in the mixture. So, here the numerator will be the partial pressure of the particular species divided by the atmospheric pressure raised to the stoichiometric value of the, or what we can say here is, in this equation for CO there is 1 kilomole. So, PCO by P naught is raised to power 1 and so on. So, now when I find the Kp value with respect to the delta G by RUT, then I get one more equation in which I connect the Kp value which is evaluated with the partial pressures. So, now let us do a small example to determine how to find the equilibrium products. Same example you have taken here, rich combustion with CO2 dissociation. So, now C7 is 16 plus 13.75 O2 plus 3.76 N2, giving, I do not know the number of moles of CO2, CO and O2. So, I just put A, B, C for them. So, A CO2 plus B CO plus 8 H2O plus C CO, C O2, C times O2 plus 51.7 times N2. So, by atom balance I get two equations, and by the equilibrium I get the third equation. Please see how I have done this. Partial pressure of CO by P naught can be written as mole fraction of CO into the total pressure of reaction divided by P naught. So, CO P by P naught power here, let us also assume that the P and P naught are different. If they are same, this ratio will be 1. So, x naught into P by P naught power 1, x O2 into P by P naught power 0.5 divided by x O2 into P by P naught power 1. So, what is x O2? X O2 is the mole fraction of O2. So, sorry, XCO. XCO is the mole fraction of CO, which is nothing but B divided by, I can say A plus B plus 8 plus C plus 51.7. So, this I call number of moles of the products. So, you can see that how I connect one more equation. See, there are three unknowns A, B and C. I found first equation like this, second equation like this. Now, taking into account of chemical equilibrium, I have formed the third equation like this. But in the third equation, I have to somehow, I am getting third equation like this so far, correct? Kp I know because I know delta G. So, with that I can write the partial pressures like this. In the previous slide, I have told the definition. Based upon definition, I have written the partial pressures, etc. But in terms of mole fraction now. So, now to elaborate mole fraction, I will say it is B for CO, it is B divided by A plus B plus 8 plus C plus 51.7, which is the number of moles, total number of moles in the product. Okay. Similarly, C divided by N power 0.5 divided by A is the CO2's mole, number of moles divided by N. Now you can see that here N and N cancels, but N power 0.5 in the denominator still remains for the C term. So, I will say P by P naught by N power 0.5. So, please understand, I have now generated three equations. I know N, I know P, I know P naught. So, Kp also is known. So, that means I have generated three equations, three unknowns. But one main problem has occurred here is the first two equations are linear, but this equation is non-linear. Do you understand? So, when I have to solve these three equations, I have to apply the solution methodology for solving system of non-linear algebraic equations. Okay, system of non-linear algebraic equations. That's what I will try to use for this. Okay, so now if I solve these three equations, I will get the value of A, B and C. That's what equilibrium does. So, now let us go by one now. So, I told you, if there is dissociation, if there is fuel rich condition, that is the equilibrium ratio is greater than 1, then also I have to get the help of chemical equilibrium to solve the problem. So, let us move on to multi-component fuels. As an example, let us consider LPG, liquefied petroleum gas. Okay, naturally occurring petroleum crude oil, when subjected to distillation, you will get LPG, gaseous component, which if compressed to about 6 bar, it will become liquefied and you can store it as a liquid in cylinders. Now, LPG is very complex, even though we can say it is a mixture of butane and propane, 70 to 30% each. But if you really do the analysis, typical composition can be this. It's a very big high number of components are present. So, you have CH4 to C5H12 are present, and here the percentage basically are indicated here. This may be varying also. See, because we liquefy this gas, when you take out some gas, when the liquid reaches the atmospheric pressure, it flash vaporizes and becomes gas. Because in the atmospheric condition, LPG will be in gaseous state. So you will see that some iso components are present, N component, that is normal components are present. Then you can say another isobar, cis 2, trans 2, etc. are also present. Then you see C3H8, C3H6, that is saturated and unsaturated hydrocarbons. So if you take this example of LPG, it has a mixture of saturated and unsaturated hydrocarbons. For the same compound, isomers are there also. Normal, this isomer, this is normal. Okay. Then you can also say trans, the bond structure variation, etc. will give these categories of molecules. Okay. So the properties of isomers and normal will generally be same for molecular weight, etc. But when it comes to say reactivity, they may be different. Okay. Because of the variation in the chemical structure, the normal and isomers have different burning characteristics. So how to first find the amount of air required to completely burn this LPG, which is a multi-component fuel? Very simple. I consider 100 kilomoles of fuel. What is given here is the volumetric composition by volume. Volumetric percentage of each component present in the species. If you add up, it will be 100. So if I consider 100 kilomole, this percentage will convert to kilomole directly. Correct. So when I do that, see, methane's volume fraction percentage was 0.03 percentage in the mixture. Now when I take 100 kilomoles, I can say that 0.03 CH4 will be there in the mixture and so on. So the red color thing, species are given, but one simplification I have done. I have not taken into account of the isomers or normal components here, but it is not required. Okay, somehow see the rate at which reaction takes place, etc. can be different, but to find how much air is required, basically I need only the carbon atoms and hydrogen atoms. So just group them and write this as the fuel stream, fuel in the reactant stream, plus M times O2 plus 3.76 N2, that is the amount of oxidizer required, giving N times CO2 plus P times H2O plus 3.76 into M times N2. So this is a complete conversion. All the carbon is converted to CO2, all the hydrogen is converted to H2O, and nitrogen remains inert. 3.76 into M, nitrogen remains. Now, we have already shown that it is customary to write an equation, global equation, in terms of 1 kilomole of fuel. But the previous equation has been written in terms of 100 kilomoles. So just divide this by 100 and write the equation once again. You will see that the fuel components are grouped like this. Obviously, you will see lower numbers. We are divided by 100. Now I say A kilomole of oxygen is required, which produces B kilomole of CO2, C kilomole of H2 and 3.76 A times N2. So this is the stoichiometric reaction for the LPG, considering the components which are listed here. Doing some simplifications that the isomers etc. are considered as normal components for the air requirement calculation. So now what are the unknowns here? Three unknowns, A, B and C. Okay, now I have C balance, I have H balance and I have O balance. So there are three equations which can be generated based upon C, H and O balances, and there are three unknowns A, B and C. So therefore, just by doing an atom balance, I can get the values of B, C and A. So A equal to 6.015, that's the value we are getting for this. Now what is the molecular weight of LPG? Molecular weight of LPG is around 54.2. Why I am trying to find the molecular weight? Because I have to find the air fuel ratio or the amount of air required to burn 1 kg of fuel. So just do this, molecular weight can be determined by this. Now basically this I have just grouped all the C and all the H and multiply the C with 12 and H by 1, that's all. So that I get as 54.2, which is much heavier than air. Air has a molecular weight of 28.84 and here it is around 55 for LPG. So once I know that, I know A value 6.015 into 4.76 into 28.84 divided by 1 kilomole of fuel, because I already considered the equation for 1 kilomole of fuel into molecular weight of fuel. So that will be the air fuel ratio, stoichiometric. So that is around 15.23 kgs. So as I told you, for several hydrocarbons, we can say approximately I need about 15 kilograms of air to completely burn 1 kilogram of hydrocarbon. So this is about the multi-component gas fuels. Okay. So now coming to the solid fuels, let us consider wood. Very complex fuel. We have already seen that it is a charring fuel. Which produces carbonaceous residue, that is carbon plus ash residue. Now using the proximate analysis, I will get the mass percentages of the gaseous components, moisture, fixed carbon and ash. These are four primary components I can get. That is, I will get a percentage of volatile, percentage of fixed carbon, percentage of moisture and percentage of ash. Now I do ultimate analysis to get the mass percentages of the elements like C, H, O, N. Okay. So these are the basic information I need before proceeding to calculate anything. This is true for any solid fuel. Okay. This is typical of charring solid fuel. It may be wood, it may be coal, anything or any other type of char producing fuel. I need proximate analysis to get information about volatile, fixed carbon, moisture and ash, and the ultimate analysis to get the elemental composition C, H, O and N. Even S, you can also add S, sulfur. These two are on mass basis. Now, this wood has to be heated to certain temperature, before which you will not be able to extract the moisture and the volatiles. Okay, now let us consider a typical wood. So now what I have done here is, let us say the wood is fully dry and very limited amount of or negligible amount of ash is present in the wood. Under the circumstances, I will say wood consists of 80% volatile. This is for any biomass. The volatile gaseous component trapped within the solid will be very high. So 76-80% like this. Then a small amount of, if it is dried, okay, so some small amount of moisture, 1 or 2% may be there. Ash also will be very less. Okay, so neglecting those two, remaining will be fixed carbon for us. So this will be the typical proximate analysis of a wood, we can say, on dry ash free basis. If the moisture content is very less, ash also is very less, then I neglect that and write the proximate analysis as 80% volatile plus 20% fixed carbon. So in the absence of moisture and the ash, the other two components are present. Similarly, ultimate analysis gives us 50% for this typical wood I am saying, 50% carbon, 8% hydrogen, 41.5% O and 0.5% N. This is the CHON. There is no sulfur also in this, so no sulfur comes out. So you can see that tremendous amount of O is also available within the wood. Within the wood means within the volatiles. In this specific particular case or in any other case, volatiles will have oxygen. But see, hydrogen, oxygen, nitrogen, etc. will be only in the volatiles, gaseous components. The fixed carbon, we are saying from the ultimate analysis, 50% of carbon, fixed carbon is present. Proximate analysis, 20% of fixed carbon is there. That means 30%, 50 minus 20, 30% of fixed carbon, the carbon will be in what? Will be in volatiles. Okay. Carbon in volatiles. So how 30% of carbon will be there in the volatile? It may be in CO, it may be in CH4, it may be in C2H4, etc. So volatiles contains these gases where there are carbon. So that is what is contributing to 30% of the carbon in this. What about 20% fixed carbon? That is solid carbon. Solid carbon is 20%. So carbon in solid form, which is there in the fixed carbon, once the volatiles go out, the 20% of the mass remaining will be solid carbon where surface reaction take place. Volatiles where carbon is present, that will burn in the gaseous reaction, flaming reaction. Okay, so now, so how to get a representative composition of the wood? Okay, let us now say if this wood is heated in inert, that is, there is no oxygen in the environment, say nitrogen, hot nitrogen, etc., then volatile is released. Then fixed carbon will be remaining. So let us see when these volatile burn, how to calculate the air requirement for that. So let us say for calculating the stoichiometric air required for the gas phase reaction involving volatiles alone, the fuel can be represented in a consolidated form or equivalent form, like it has some X atoms of C, Y atoms of H, Z atoms of O and the P atoms of N. Okay. The moles of C, H, O and N are X, Y, Z and P respectively. But to evaluate this, I need information from both proximate and ultimate analysis. Okay, for doing this, I need some typical value of molecular weight of the volatiles. Typical value. So studies have shown that the volatile species which is trapped in solid fuels have species like CH4, C2H2, C2H4, CO, H2, O2 and N2. Say some sulfur also will be there. Sulfur oxides can also be there, but negligible, not much. But in the solid part, there may be some sulfur. So you can see this components will be having some proportions or some fractions. But typically studies have shown that the considering the proportions of these species, the molecular weight of volatile mixture will be around 30 kg per kilomole. Typically, okay. Exactly to find the species composition, we need gas chromatography, etc., or mass spectrometry. So what we do basically is we try to find these composition for several volatiles, but that depends on the rate at which volatiles come out, the heating rate and so on. Okay, but in a simplified analysis, we need not go for that exact composition of the species contributing to the volatiles. So what I do, what I do is I take a typical molecular weight for volatile as about 30 kilogram per kilomole. I don't go for any complex analysis. So with that, I can do the following. To evaluate X in the consolidated fuel, that is Cx, I will say weight of carbon in volatile divided by molecular weight of the carbon divided by weight of volatiles in wood, the total wood divided by the molecular weight of volatiles. Okay, so now go back. In this case, I have 80% volatiles, 20% fixed carbon. That is the proximate analysis. And ultimate analysis, 50% carbon is there. Okay, now weight of carbon in volatile will be 50, which is the total, minus 20 will be the fixed carbon. So I have to remove the fixed carbon content. So 50 minus 20, that is 30, divided by 12 molecular weight of the carbon divided by weight of volatiles, that is 80% of wood is volatile, 20% of wood is fixed carbon. So 80 by molecular weight of volatiles, that is 30. So X is evaluated as 0.9375, 0.9375. Similarly, you go for hydrogen, but in hydrogen there is nothing in the fixed carbon. Okay, so everything will be in volatiles. So 8% hydrogen from the ultimate analysis, the total value, that is the weight of, instead of carbon you put hydrogen here, weight of hydrogen in volatile divided by molecular weight of hydrogen divided by, the denominator is the same. So here weight of hydrogen in volatile is 8 divided by molecular weight of hydrogen is 1 atom divided by 80 by 30, that is 3. So do it for other two, oxygen O atom and the nitrogen atom. So if you do this, I get numbers like this for Z and P. Now just take some significant digits after the decimal point and represent the volatile as C 0.94, H3, O 0.97 and N 0.013. Okay. Now making the atom of C as 1, I can just divide the entire numbers here as decreases by 3.94. That is, C is written as 1, H instead of 3 I am writing as 3 by 0.94, approximately 3.2, and I am rounding off also. Similarly, O 1.03 and N 0.014. So here the number of atoms of C is kept as 1. So calculated molecular weight, it is about 31.88. Typically, I was told that molecular weight can be taken as 30. So no issue. Similarly, nitrogen is 0.014. So I can neglect that also. And round off the value for H and O as 3 and 1. So that typically I get C, H3 and O for the volatiles. Equivalent volatile composition with a molecular weight of 31, so which is well within the assumed value of 30. Okay, so now for this equivalent fuel CH3O that represents the volatile, I can write the stoichiometric equation as CH3O plus 1.25 times O2 plus 3.76 into, giving all the C goes to CO2, H3 goes to 1.5 H2O, and please understand that this O is already present. So I need to supply only O which is in addition to this O what is already present. Do you understand? So this is what the equation is. So if there is no O here, there is no O, what will be the value of A? This is actually A is now 1.25. So what will be the value of A if there is no O? It will be 1 plus 3 by 4. That will be, pretend that this O is not there, only CH3, then it will be 1 plus 3 by 4, that is 1.75. But due to the presence of this O, I am writing A as 1.25. So the fuel bound O will be taken into account to calculate the stoichiometric. So for stoichiometric air, I should not put the value excluding this O. Okay, the complete combustion should be assumed as usual. So now when you calculate the stoichiometric air fuel ratio for burning volatiles, it will be around 5.535 kg of air per kilogram of volatile. Okay, so oxygen inherent in the fuel contributes to notable proportion of the combustion. Okay, for burning unit mass of the wood, including both volatiles and fixed carbon. So now I am not separating volatiles out, just to burn the entire wood. I can write the concentrated fuel again in terms of Cx, Hy, Oz and Np. Now the calculation is straightforward. What is the X? X is 50% of, just take ultimate analysis only now, because we are burning entire thing. So the elemental composition is present in the ultimate analysis. So 50%, so that is 0.5 by 12, 8%, 0.08 by 1, Z is 0.415 by 16 and P is 0.005 by 14. So the controlled fuel, neglecting nitrogen and taking one carbon atom, can be written as C H 1.92 and O 0.63. For this, the single step reaction can be written like this, considering this O also which is present in the fuel, excluding that, writing the excess oxygen required to completely burn C to CO2 and H to H2O. We say that the stoichiometric air for burning wood will be about 6.66 kilogram of air per kilogram of wood. So that is the stoichiometric air required. Okay, so I'll stop here.